Welcome to the third lecture in discrete optimization. This is the first of two lectures actually in which we are going to treat maximum flow problems. The first of these two lectures is going to be about more structural results on flows in networks, while the second one is going to be about algorithms to actually compute maximum flows in networks. So this is what we do, maximum flow computation. And here is a short overview of this lecture number 3. I'm going to start with some basics on flow problems and maximum flow problems. I will be talking about so-called augmenting paths to increase the flow value of a given flow. And then at the end, I talk about a structural result, a very classic result, the so-called maximum flow minimum cut theorem. That is a duality result actually, which says that the value of a maximum flow in a network is always equal to the value of a minimum cut in the same network. Now, when I talk about maximum flow or flow problems in general, what should you have in mind? And the best thing, the easiest thing to illustrate that problem is the following. So what we are going to treat is so-called static network flow problems. And the way you should think about that is that you are given a network, a fixed network that consists, say, of tubes and connected tubes. And there is a certain point in the network where you insert pressure or a liquid, and you wonder how much liquid can you push through this network. Just like in this given example, so we have this hydrant here, and it pushes water or some liquid into this network of tubes. So think of these green connections as tubes. And for the time being, we could say that there is 1 liter of liquid which can go through any such tube at any point in time. And then we would be wondering how much liquid can we actually pour into the bucket per unit time. This is obviously just one example. Pumping a liquid through a given network, like in this little picture here. Another very classic example would be traffic flows, where the network would be the physical streets, highways, and so on. And you wonder how much traffic can go through a part of a network in a city, for example. So that's also a very classic problem and a very important application for network flows. So notice that this is about so-called static flows. We are pumping the maximum capacity, and then we are pumping at that capacity at any point in time. So we are talking about a flow per unit time here. And when you think of the traffic example, we are not talking about actually the single car and how much time it takes to get the car from A to B. So that's not what we are talking about here. On this little picture here, I can also illustrate already nicely the maximum flow minimum cut theorem that I was referring to. So you see this little scissors here. So the amount of flow, the maximum amount of flow that I can actually pump into this bucket here is equal to the minimum amount of tubes that I could try to disconnect using the scissors here. And if you want, you can try to figure out how many of these little green tubes I would have to cut in order to disconnect this network. Now let me come to the mathematical definition of a flow in a network. So we are given a directed graph, G. E is a set of directed edges, and each of these edges has a non-negative capacity C. Okay, so that's the amount of flow that can go through this edge at any point in time. And we have a designated source vertex S, and we have a designated target vertex T, and we would like to compute the maximum flow that can go from S to T. Now, as a matter of fact, we can assume without loss of generality that the graph is complete. So all the edges are there, because otherwise we could just as well add zero capacity edges without changing the problem. Okay. We can also assume without loss of generality that all the vertices are reachable from S. Otherwise, we could as well eliminate such vertices. Now, what is the definition of a flow in a network? And a flow from S to T, or an ST flow, is just a function that assigns a flow value to each of the directed edges of the graph. fulfilling the following three constraints. First of all, on each of the edges of the graph, so for all edges of the graph, I have to fulfill the capacity constraint, which just says that the flow value cannot be more than the capacity of that edge. That is clear. Then we have a definition here of skew symmetry, and I will explain that in a minute. So skew symmetry just means that the flow from U to V, from vertex U to vertex V, is just the same as minus the flow from V to U. This definition is simply convenient, and it actually refers to the fact that we are interested in the net flow from U to V, and I will explain that on an example in a second. And finally, we have a constraint which is called flow conservation. So flow conservation says the following: for all the vertices U other than the source and the target vertex, it is actually the case that this vertex U does not produce or consume anything. Okay, so most intuitively, that is saying that the positive flow going into a node must be equal to the positive flow going out of that node. And because of our definition here of skew symmetry, we can formulate it in this way, saying that the flow out of a vertex U, that's the total flow out of the vertex U, is just equal to 0. So let me illustrate these definitions on a few examples next. So first, let's look at skew symmetry. Look at this little example up here. Okay, so if we have a flow, for example, out of a vertex S into vertex U of 2 units, and in red here you see the capacities of the edge. And we also would have a flow in the opposite direction of 1 unit from U to S. Then, as a matter of fact, the net flow from S to U is just plus 2 minus 1 in the opposite direction. So the net flow would be plus 1. And the net flow would be minus 1 in the opposite direction then by symmetry, right? So it's simply more convenient for all what we are doing in this lecture to just work with the net flows. So instead of considering this picture up here or this situation up here, we would say, okay, the proper definition of a flow is to have this 1 unit net flow from S to U, and then minus 1 unit goes from U to S. So once we have fixed this convention, we define a flow to be feasible if it fulfills skew symmetry, and that just means that the flows in opposite directions are just negatives of each other. Okay, so we have looked at skew symmetry. Now let's look at the flow conservation constraint, the third one here. So the constraint says that the total flow out of a node U is equal to 0. So let's look at a little example also for that. So let's concentrate on this vertex U in this figure here. So there is actually a positive flow of 1 unit going into this vertex U, and there's a positive flow of 1 unit going from U to T. So it's as simple as it could be. And then by skew symmetry, we have to define the flow in the opposite direction to be the negative. So minus 1 from U to S and minus 1 from T to U. Now flow conservation means that the total flow out of U should be equal to 0 under this assumption of skew symmetry. And what is the flow out of U? Well, that is this, that is this 1 unit of flow going out of U to T, and that is this minus 1 unit going from U to S, so that the flow out of U would be plus 1 minus 1, indeed equal to 0. And also for the flow into node U, we have the same. It would be 1 unit from S to U and minus 1 unit from T to U. So that is again plus 1 minus 1 equal to 0. I think the more intuitive way of seeing flow conservation is the following. It's that the positive flow, it's that the positive flow out of U is just equal to the positive flow into U which exactly means that the vertex U does not produce and neither consume anything. Okay, so let us just quickly see that this is exactly the same. So what I've written down here is the positive flow out of node U. So that's all the flow values from U to V, for positive flow values for all the vertices V. Now by skew symmetry, so that was our constraint number 2 actually, the flow from U to V is minus the flow from V to U. So let's do that. Now we are summing here over all positive flow values in the graph. And when is the flow value positive? Well, exactly then when it's negative in the opposite direction. So therefore, this is the same when I just sum over all the edges with a negative flow value. So the summation remains the same. I'm just now summing over all the F from V to U, which are actually negative. So that was again our definition of skew symmetry. And now flow conservation says that the total flow into node U is equal to 0. Okay, so if I sum over all vertices flow from V to U, that is equal to 0. And this sum here is the sum of all the positive and all the negative flows into U. And therefore, this, by flow conservation, this must be equal to the flow from V to U, now positive, flow from V to U. And this is exactly the positive flow out of into node U. Notice that flow conservation is a constraint that has to hold for all the vertices in the graph, but of course except the source and the target vertices. Since we want to send flow from S to T, these two vertices S and T are not fulfilling the flow conservation constraint. Okay, so we have defined what a flow in a network or in a directed graph actually is. It has to fulfill capacity constraint, skew symmetry, and the flow conservation constraint. Now, given this definition, we can continue, for example, defining the flow value from a subset X to a subset Y of the vertices of the graph by just summing up of the corresponding flow values for all the involved vertices X and Y. Okay. Now with this definition, we can collect another few observations. First of all, by skew symmetry, we have that the flow value from set X to set Y is just a negative from the flow value from Y to X. That should be clear. Then from this observation, we can immediately conclude that the flow value from a set X to itself must be equal to 0, simply because we get from 1 that flow from X to X is equal to the negative of the flow from X to X. So hence it must be equal to 0. And finally, if I have two subsets X and Y, which are disjoint, and I look at the flow value from the union of X and Y into a subset Z, then this is just the sum of the flow values from X to Z and from Y to Z. This of course holds just by linearity and because these two sets X and Y are assumed to be disjoint. Final remark, so once I have made this definition, flow value from arbitrary subset X to an arbitrary subset Y, there is also a very convenient way of writing down the flow conservation constraint. Namely, it now just means that for an arbitrary intermediate vertex U except S and T, the flow from U into all the other vertices V is just equal to 0, and also the flow from all the vertices into U must be equal to 0. Okay, so this was just notation. So what's the problem that we are going to look at? So here comes the definition of our object of interest, the maximum flow problem. So we define the value of a flow as the total flow value out of the source vertex S. Okay, so that's the total flow that goes out of S into the rest of the graph. Okay, because all the other nodes except S and T have to fulfill flow conservation, so the flow cannot disappear in the network, and therefore the flow out of S must be equal to the flow into T. I'm going to show you a little proof of this as a small exercise in a minute, but the definition of the problem is we are given a directed graph, we are given edge capacities, non-negative, source node and a target node S and T. We want to compute an ST flow in the network of maximum value. So how much flow can be transported through this network from S to T, fulfilling all the capacity constraints. Now I was claiming that the flow out of S must be equal to the flow into T. Intuitively, that is clear by flow conservation of all the intermediate nodes of the network. But let's, as an exercise, look at the proof of this little statement. So the claim is the flow out of S must be equal to the flow into T. And I start writing down what the flow out of S is. Well, that is the flow from S to all the other nodes in the graph. I'm essentially just playing a little bit with the definitions and little observations that we made before. So this is equal to the following: flow from V to V minus the flow from V minus S to V. This is because our flow function is a linear function, and the two subsets V minus S and S are actually disjoint. Now the flow from V to V is actually equal to 0. So this is just equal to minus the flow from V minus S to V. And by skew symmetry, this is equal to the flow from V to V minus S. Now this subset of nodes, V without S, also includes the target node T. So let me just split that up again in the same way like I did before. So this is equal to the flow from V to T plus the flow from V to V minus S minus T. Now what is the flow from V to V minus S minus T? Let me just write down what that actually is. So that's just the sum over all vertices U not equal to S or T. And then the flow from V to U. But by flow conservation, we know that this thing here is equal to 0. So therefore this whole thing is equal to 0. And hence, this is equal to the flow from V to T, which is just the flow into T. All right, so let's have a brief look at an example. So here's a directed graph with 6 vertices, source vertex S, target vertex T as usual, and the numbers along the edges represent the capacities of the edges. So this would be a feasible flow for this particular network. So notice that the thickness of the edges corresponds with the flow value along that edge. So for example, here we are using 11 of the capacity 16. Here we are using the full capacity 12 of 12, and so on and so on. Now, one important notion when we want to compute flows or maximum flows is that of a residual capacity. So what I mean is the following: suppose you give me this flow and I wonder, can I send additional flow from S to T on top of the flow that you gave me. Okay, so the least thing that I have to know is what is the remaining capacity along all the edges of the graph. And then I can try to see if there is maybe potentially additional flow possible from S to T. And that's exactly what we need. So we define the residual capacity of an edge with respect to a given flow F as just the remaining capacity given the flow F that is already there. So it is the capacity along the edge UV minus the current flow value from U to V. Okay, so that's the residual capacity, and it actually represents the additional flow that can be sent along that edge from U to V. And that is by definition non-negative because the flow was supposed to be feasible. Okay. I call an edge a residual edge if it has strictly positive residual capacity, okay, strictly larger than 0. And if this is equal to 0, that means such an edge is saturated. So I'm using all the capacity of that edge already, and hence this edge is called a saturated edge. And now the definition of the residual graph, given some initial flow F, that is just a subgraph of the original graph, which has as all the edges, only the edges with strictly positive residual capacity. Okay, so that's an object of interest because that kind of represents all the potential edges that I might still be using in order to increase the flow value, for example. Now let's look at the same example again. So here is the flow that we already had. Let's check, for instance, there is a flow of 11 from S to P, hence the residual capacity in the direction from S to P should be 5. Or there is a flow of 12 on the arc or on the edge from P to Q, hence the residual capacity along that edge is 0. This edge is saturated, so it shouldn't be part of the residual graph. But notice one thing. If I'm actually sending 12 units from P to Q in the opposite direction, I suddenly get a residual capacity because I could decrease the flow value in the direction from P to Q, and that would mean increasing the flow value in the opposite direction. Okay, so here is the corresponding residual graph for the given flow that I showed you on the previous slide. We see that, for instance, the flow from S to P was actually 11, the capacity was 16, hence the residual capacity of this edge here becomes 5. I was sending a flow value from S to P of value 11, hence I could decrease the flow in the opposite direction, therefore the capacity of the residual edge in the opposite direction must be 11. And as we already said, in the direction from P to Q, the edge was saturated, and therefore this edge is not present in the residual graph. But of course, the opposite edge is present in the residual graph with a capacity 12. Now remember, this residual graph is defined for a given flow F. Okay, so with the intention to figure out what the remaining capacity in the network still is, and with the intention to figure out if we can potentially send additional flow from S to T. And the next lemma exactly formalizes this idea. It works as follows. So if F is a flow in the network G, I consider a flow G, which is a feasible flow in the residual graph. So it respects the residual capacities. Okay. So then the claim is that I can combine these two flows together. So I just take the sum of F and G. I called it H here. And the claim is that this is actually a feasible flow in the original graph. And of course, it will have, because of linearity, the value is just the sum of the values of the two flows F and G. So the lemma says that the sum of these two flows is again a feasible flow. So I have to verify the 3 conditions for feasible flow. So they have to respect the capacity constraints, they have to be skew symmetric, and they have to respect the flow conservation constraint. Now, 2 of these things are trivial because this is a skew symmetric vector and this is a skew symmetric vector. The sum of the 2 is again skew symmetric by definition. And also F fulfills flow conservation constraint for all the vertices, for all the intermediate vertices except S and T, and G as well. And the sum, 0 plus 0 remains 0. So the sum of the two flows still will respect the flow conservation constraint. So the only thing that we have to think about is actually the capacity. So let's see how we can see that. So why does this sum of these two flows fulfill the capacity constraint? Also, that is not difficult. So first of all, we have to observe that G was defined as a feasible flow in the residual graph. So it respects the residual capacity. H is just the sum of the two flows. So now I just plug in what I know about flow G, namely flow G respects the residual capacity. Okay, so the flow value for G is at most the residual capacity. So I get this inequality here. Now I just plug in the definition of residual capacity. What was that? Well, the residual capacity was the original capacity minus the corresponding flow value, right? Now I just cancel out equal terms here, and I get the capacity, the original capacity of the edge, and hence the sum of these two flows, F and G, respects the original capacity. So what does this lemma give us? Given an arbitrary flow, initially could be 0, I can compute the residual graph. That is very easy in linear time. And I can compute a flow in the residual graph and add it to the flow that I already had, and I obtain a flow which has a larger value. So that's a viable way to go for designing algorithms. And what we're actually doing most of the time, not always, is that this additional flow G in the residual graph will be just a very special flow, namely a flow on a single path, and that's called an augmenting path. Okay, and using augmenting paths, we have also a very nice characterization of maximal flows, so optimum solutions to our problem. So that's actually what we do next, characterizing maximum flows by augmenting paths. So what is the definition of an augmenting path? Well, an augmenting path is just a simple path in the residual graph, a simple path from S to T. And we define the residual capacity, Rf of P, as the maximum capacity or the maximum flow that we can get through this simple path. Okay, and that is actually determined by the minimum capacity along that path, right? Notice that this is still strictly positive because all the capacities in the residual graph are strictly larger than 0. So if everything is integer, they are at least 1. Now, once we have found an augmenting path in the residual graph, we can actually augment the flow by sending the maximum amount along that path. Okay, so we can augment the flow F along the path P, along the augmenting path P, by that many units, that is the residual capacity of that given path. And we obtain a new flow by just defining the flow F prime to be equal to F almost everywhere. And only we augment the flow values along the path P. So if an edge lies on the path P, we increase the flow by the residual capacity, and the edge in the opposite direction, we decrease the corresponding value in order to maintain skew symmetry. Now, in order to show that the so augmented flow F prime is still a feasible flow, we only have to show using the previous lemma that the path flow along the path P is actually a feasible flow in the residual graph. And in some sense, that just directly follows from the definition, but it doesn't hurt to quickly recap why this is true. So here G now denotes the flow on the augmenting path P. That means that on all the edges of that path, we are sending an amount equal to the residual capacity of that path. And of course, in order to maintain skew symmetry, the edges in the backward direction have a flow value minus the residual capacity of that path. So this is exactly how the situation looks like. when the path goes from S to U to V to T. So we have flow values equal to the residual capacity on the forward arcs and minus that capacity on the backward arcs. Now, if we look at the forward arc from that path, then the actual flow value from U to V is just equal to the residual capacity of that path, so Rf of P. And since the residual capacity Rf of P was chosen to be the minimum capacity along the whole path, this is not more than the capacity of the corresponding arc UV, right? Rf from U to V. And if we consider a backward arc from the path, then the situation looks as follows. The corresponding flow value from V to U is minus the residual capacity of the path. And that is certainly smaller than 0 because the residual capacity is strictly larger than 0. And we know that the residual capacities are always non-negative. So this is also upper bounded by the residual capacity of the edge from V to U. Now, skew symmetry just holds by definition because we defined flow G to be skew symmetric. And also flow conservation is actually fulfilled because for all vertices U on the path, we have that the flow from U to all the other nodes is equal to the flow from all the other nodes to U. Is just equal to, we have once the residual capacity of the path minus the residual capacity of that path, right? If you look at an arbitrary node U on that path, there is one ingoing flow positively and one ingoing flow negatively, and the same for the outgoing flow. Okay, and that is obviously equal to 0. Okay, let's see how flow augmentation along augmenting paths actually works on a little example. So here we have the graph that I already showed earlier with a given feasible flow in that graph. And as you can see, we have, for instance, ST paths in this graph. So there's one up here, okay? But this ST path actually doesn't have any capacity left. So if I want to send flow on top of the given red flow here, I will see that the edge up here from P to Q, that's a saturated edge. It has no capacity left, so I cannot augment the flow by sending along this path. I can also not augment along this path, and so on and so on. But as a matter of fact, if you consider this arc here from Q to U, we could actually decrease the flow along this arc in this direction, which means increasing the flow in that direction. And taking that into account, we can actually identify an augmenting path along these vertices here. And that is much easier to see if I just look at the corresponding residual graph. Because in the residual graph, this just corresponds to a simple ST path. Okay, so here we identify this simple ST path from S to T, and we can also already identify what the corresponding capacity along this path is. So this has a capacity, residual capacity of 5. Here the residual capacity is 4, and here it is 5 again. So the residual capacity of the corresponding path would be the minimum of these values. So that's the maximum amount that can go through this path. Also, if you look at the upper path that I indicated before, you see that this does not correspond to a simple path in the corresponding residual graph. So we have found a simple ST path in the residual graph, and this would be the corresponding path. And now the only thing that we do is we take the original flow vector and we take the corresponding flow vector that corresponds to augmenting the flow along this augmenting path. And that looks as follows. So here is the flow that we started with, that is F. Here we define a corresponding skew-symmetric flow corresponding to a flow along this augmenting path. By which amount? Well, by the amount which is equal to the residual capacity along this path, which was actually determined by this edge in the middle, right? Now, flow vectors are just vectors, so I just add these two vectors, f and g. And the previous lemma says that, well, if g was a feasible flow in the residual graph, then the resulting flow will again be a feasible flow in the original graph. And that's also what we get. So let's make a few checks and balances. We started with a flow here, with a flow value 11 plus 8 was 19. We were augmenting the flow along this path by how much? Well, capacity of the residual path, the residual capacity of the path. So that was 4. And hence we should obtain a flow with value 19 plus 4, that is 23. And this is also true. So if I look at the outgoing flow for vertex S, that is 11 plus 12, which is 23. So let us summarize what we did in a little lemma here. So if we have given the flow F, and P is an augmenting path for that flow F, so that's a simple path in the residual graph, we define F prime to be the flow that we get when we add the path flow along the augmenting path to F. So we augment the flow along this path P by the residual capacity of the path P. Then the resulting flow F prime is just again a feasible flow in the original graph, and the value of that flow will have increased by exactly the residual capacity of that path. So in particular, we will have increased the flow value. So what did we do in order to prove that lemma? The only thing we needed to show is that the flow G, defined by the skew-symmetric flow along that path P, is a feasible flow with respect to the residual capacities. So it's a feasible flow in the residual graph, and that is exactly what I just did. So out of this lemma, an algorithm to compute maximum flows almost suggests itself, right? Because we know as long as we can find augmenting paths in the residual network, we can increase the flow value by sending flow along these augmenting paths. And the question is, does that actually work? So if I augment flow along augmenting paths successively, and at some point in time, this is no longer possible, do I actually compute a maximum flow? Yes or no? The answer is yes. And that is stated in this theorem. So a flow is a maximum flow for the graph G if and only if the corresponding residual graph GF has no augmenting path anymore. So that means that the algorithm that I was just proposing, namely sending flow along augmenting paths until no longer augmenting path can be found in the corresponding residual graph, that is a feasible algorithm to do. So as to the proof, most of it is already done. So the only if part we already did, because I just argued in the previous lemma that when there is an augmenting path in the residual graph, then we can actually augment the flow. So the flow was not maximal. And for the if part, we do the following. We assume we have a flow F, and this flow F has no augmenting path in its corresponding residual graph. But for contradiction, we assume there exists another flow F star, which has a strictly larger value. And I will have to get a contradiction by arguing that if such a flow F star exists, well, then we can actually also find an augmenting path in the residual graph for F, and that's a contradiction. So we have F, that's a flow without an augmenting path in its residual graph. We have F star, which is our assumed flow, which has a higher flow value, larger than that of F. And in order to get the contradiction, I look at the following. I define H to be the difference of these two flows. I mean, F star and F are just flow vectors, so I can subtract one from the other. what is the value of that difference flow? So what is the value of the flow H? Well, that is the value of f star minus f, and everything is linear, so that's the value of f star minus the value of f. And our assumption was that this is strictly larger than 0. So that means that this difference flow H, f star minus f, is actually a flow from S to T with a positive value, and hence it contains at least one path from S to T. And if I now show that this difference flow H is actually a feasible flow in the residual graph for f, that means that this ST path here is also a path which is actually present in the residual graph for f, and that will be a contradiction because we assume there is no augmenting path in GF. So the only thing we have to show is indeed that this difference flow H is indeed a feasible flow in the residual graph for f. So we need to show first, that the capacity constraints are fulfilled. So what is the flow along an edge from U to V? That is just F star from U to V minus F from U to V. So that is smaller or equal than the capacity from U to V minus the flow value from U to V. And that's exactly the residual capacity of the edge from U to V. So the flow value of this difference flow H is at most the corresponding residual capacity, so it's feasible for the residual graph for f. And now the rest of the proof is essentially a simple writing exercise. So what about skew symmetry? Well, the difference flow from U to V is just defined as f star from U to V minus f from U to V. And these two guys actually fulfill skew symmetry, so that is equal to minus f star from V to U minus f from V to U, and that is just minus h from V to U, so it's actually also skew symmetric. And finally, flow conservation. So if we take a vertex U not equal to the start or target vertex, then we have that the flow from U to all the other nodes is just equal to the flow f star from U to all the other nodes minus the flow f from U to all the other nodes. But this is equal to 0 and this is equal to 0 because f star and f fulfill flow conservation, and hence this is equal to 0. And that's it. So what did we actually show? Well, if we have a flow f and we assume there exists another flow f star which has a strictly larger value, then there also still exists an augmenting path for flow f, and therefore vice versa, once we have a flow f without any augmenting path, this must be a maximum flow. So we have found the characterization of maximum flows by means of augmenting paths. So whenever there is no augmenting path in the residual graph, that means we have a maximum flow. All right, so we have seen one characterization of maximum flows, namely via the non-existence of augmenting paths in the corresponding residual graph. And the rest of the lecture is about another characterization of maximum flows, namely via so-called minimum cuts in the network that achieve the same value. So that's actually the famous maximum flow minimum cut theorem, a special case of duality. But before I do that, let me squeeze in a little historical remark about maximum flows and minimum cuts. So what you see here on this picture is a part of Eastern Europe. So for example, here would be, here would be Poland approximately. This is a part of the Soviet Union, now Russia. Here you see East Germany, back then called the GDR. Maybe some of you remember that. And what you also see on this picture is a couple of origins, which are labeled here. And so what is the meaning of this figure? So the Soviet Union in that time, it was the time of the Cold War. So if you look at the year here, that is 1955. So it's from a publication from 1955. The Soviet Union was interested in determining the maximum transportation capacity of military material from the places where this military material was actually located towards East Germany. And if you think about transportation of military material, I think we have to think of tanks here. Now, if you look closely, you see that this picture is taken from a publication by Harris and Ross, and actually that is Generals Harris and Ross from the US Air Force. So obviously the US Air Force was not interested in the maximum transportation capacity of tanks towards East Germany. They were interested in the dual problem of that, namely determining the cheapest possible way in order to prohibit transportation of tanks into East Germany. And if you look very closely, you see here a label which says the bottleneck. And that bottleneck, let me highlight that, is this one. And that would be the cheapest way in order to prohibit transportation of any tanks towards East Germany. So the cheapest way to disconnect this whole network here so that no tanks could arrive in Eastern Germany. So the historical footnote here is actually that both the Soviet Union and the United States were interested in almost the same problem, actually the duals of each other. Now, this is a publication from 1955, and you can imagine that back in that time, it was still the time of the Cold War. This was certainly classified information. And that is actually true. So back then it was classified, and it was actually declassified from the Pentagon only in 1999, so some 20 years ago, on request of our dear colleague lec03 from the CWI in Amsterdam. Now, if you should think also 1999 is really long ago, I wouldn't agree, because that was a time when I was already a PhD student in Berlin. In any case, there is a historical connection about computing maximum flows, in this case towards East Germany, and minimum cuts in the corresponding transportation network. But not also is there a historical connection, there is also a mathematical connection. As I said, these two problems are actually duals of each other. And in order to see that, we have to define the notion of cuts. Now, first of all, we define for any two subsets, x and y, of the vertices of the graph, the maximum capacity that could be transported from x to y. So this C of x comma y is just the sum of all the upper capacities of all the edges that go from the set x to the set y. Okay. Now, having defined this, we call a subset of the vertices an ST cut, or simply a cut for simplicity. If it is a partition of the vertex set into a subset X, and actually the complement of X, such that the source vertex S is sitting in X, and the target vertex T is sitting in the complement of X. Okay, so we just partition the set of vertices into X and complement of X, and we call such a thing a cut. Okay, now the capacity of a cut is then just defined as the capacity that could potentially or maximally go from the set X to the complement of X. Okay, so that is just by definition the total or the sum of all the capacities of the edges that are leaving the subset X. Let me just illustrate that using a little example here. So we have a graph G, and the set of vertices is partitioned into a subset X and into a subset complement of X, such that the source vertex is sitting in X and the target vertex is not sitting in X, so it's sitting in the complement of X. Okay, so at least the target vertex is sitting in the complement of X, but potentially other nodes. All right. Now the capacity of that cut would just be the total sum of the capacities of the edges leaving X, so from X to X bar, and that would be actually these three edges, and the capacity of that cut would correspondingly be 3 plus 5 plus 1. Notice that there is also a backward edge here, so this doesn't count into the capacity of the cut, since we are interested in the maximum capacity or potential maximum capacity that could be transported from x to the complement of x. Now that is the capacity of a cut, and what we will show and what is intuitively also clear is two properties of cuts. So given an arbitrary flow in the network F and an arbitrary cut in the network, and remember a cut means that the source vertex sits in X and the target vertex sits in the complement of X, then the flow that is actually leaving the left-hand side X is also equal to the value of the flow, right? Because that flow has to go somewhere. It has to cross the cut, and therefore the flow value from X to the complement of X must be equal to the value of the overall flow. And the value of the flow from X to X bar is actually upper bounded by the capacity of the cut. It can never be larger. Both should be intuitively clear. But let's first look at an example. So the same graph again. So now suppose on top that we are having a flow going out of the source vertex, and the total amount that is going out of S is 4 plus 4 is 8. So the flow value would be 8. Remember that the capacity of the cut is 9. And since this flow of 8 has to go somewhere and it cannot get lost in any of the intermediate nodes, this flow of 8 also has to cross the cut, right? So that means that the flow from X to the complement of X must also be 8 in this example. So let us look at a few more examples of cuts. I take the example that I already used earlier. So given is this network and given is a certain flow F in the network, and now I just throw in a couple of cuts and let us just collect and use the definitions that I just made. So here's the first cut. So I just cut the network on this line here, and let's just see what the flows and the cut values are. Okay, so there is a flow on this edge crossing the cut of 12. There is a flow on this edge crossing the cut of value 11, but there is also a flow going in the backward direction across this cut of value 4. So that makes as a flow value from X to X bar 12 plus 11 minus 4, and that should be 19. Now, what is the capacity of the corresponding cut here? Well, that is just the capacities of the forward edges of the cut, so the maximum capacity that could cross this particular cut, and that would be 12 plus 14, which makes 26. Now let us look at yet another cut in the network. So now I have shifted the cut a little bit. So now the cut goes like this. It still disconnects S from T. And well, what is the flow value? Actually, I don't have to recompute it because it should still be 19. We already know that the source vertex is actually getting rid of 11 plus 8, that is 19 units, and everything must reach the target node T. But let's just do that again. So for this cut, we would have 12 plus 7 plus 4 makes 23, but minus 4 units that go in the reverse direction. So again, we get the flow value 19 as expected. And what is the capacity of this cut? Well, we again just collect the capacities of all the edges that cross the cut in this direction. So that would be this one, and this one. So that would be 12 plus 7 plus 4. And in this case, the capacity of this cut is no longer 26, but 23. So far everything is as expected. The flow values across the cut, they are always 19 because the flow value is just 19. And the capacities of the cuts are larger than 19, 26, and 23, respectively. But now remember that we could augment this flow by sending an additional 4 units actually along this augmenting path here. Okay, so let's look at the situation when we have done that. So now I'm changing the flow in the network, and the new flow is this one after the augmentation has taken place along this augmenting path here. Now, since we have augmented by 4 units and the flow was 19 before, the new flow value should be 23, obviously. Let us look at the two cuts that we had looked at before. So the first cut was this one. Now the flow value should be 23. Is that actually true? Yes, because we have 12 units along this arc and another 11 units down here, which indeed makes 23. And what is the capacity of this cut? Well, the capacity of the cut hasn't changed. It is just, again, 12 plus 14, and that is 26. Still, flow value is below the cut value as expected. And if I now look at the other cut that we had before, so the cut that separates the network along this line here, then we see, well, the flow value is certainly still 23. And what is the capacity of that cut? Well, the capacity of this cut was actually 12 plus 7 plus 4, which is also 23. Okay, so what we observed is that the flow values across the cut are always below the capacity of the cut as expected. That is essentially by definition of the capacity of the cut. But we have also found a cut, namely this one, for this flow, where these two values are equal. So flow value is equal to the capacity of the cut. And that should be an optimality certificate, and that is actually also true. So let me just also formally recollect the observations that we made. So if we are given a flow in the network and we are given a cut in the network that separates the source from the target node, then the flow leaving the left-hand side X, which contains the source node, must be equal to the value of the flow. I mean, that was intuitively already clear, but I can also write down an algebraic proof of that fact. So let me do that. So we are looking at the flow from X to X bar, actually. So this is just X bar. That's the complement of X. Now by linearity, I know that I can write this as the flow from X to all the set of nodes minus the flow from X to X. But we already know that this is equal to 0. So we end up with a flow from X to V. And now we just split up this term into the flow from S to V plus the flow from X minus S to V, right? Now, but what do we have here? So that's the flow from X minus S to V. That's a subset of the nodes that does not contain the source and also does not contain the target node, because the target node is contained in the complement of X. And therefore, if I write it down explicitly, that goes over all the nodes in X minus S, and that would be the flow from U to V. But we know that flow conservation must be fulfilled for all these nodes U here, right? So because this is all intermediate nodes, and hence this is equal to 0, and therefore the whole thing is equal to 0. So that means we end up with a flow from S to V, which is just exactly the value of the flow. So the flow across the cut in any network is always equal to the value of the flow, and that follows by flow conservation. And the next lemma is to reconfirm what we already observed, namely that the flow across the cut from X to X bar cannot be more than the capacity of the corresponding cut. Also, by definition, that should be clear, because the capacity denotes the maximum flow that could go across the cut. And also that proof is kind of trivial. So if I write down the flow, that's the flow from X to the complement of X. We already did that in the previous proof, right? So that is just all the flow values collected for all the edges from X to the complement of X. And we know that these flows are feasible flows, so they must fulfill the capacity constraint. So the flow value is upper bounded by the corresponding capacity. And now this sum here is just exactly the definition of the capacity of the cut. So that is also known as weak duality. So for each so-called primal solution that's a flow in the network, the value of that solution, that is the value of the flow, is upper bounded by the corresponding value of the dual solution, and the value of the dual solution is actually the capacity of the cut. All right, so we know that the value of a flow across a cut is always upper bounded by the capacity of a cut. So there is a smaller equal here, but does there also exist a flow and a cut where they are equal? And that is actually true, and that is the main theorem of this lecture. So if we have a flow, then the following bullets are actually equivalent. Well, the first two we already know. So if F is a maximum flow in the graph, that is true if and only if the corresponding residual graph has no augmenting path. But now we add a 3-bullet point here in this characterization of maximum flows, and that is the existence of a cut in the graph that actually achieves the same value. So the existence of a cut X such that the capacity of the cut is equal to the flow. Sorry, the value of the flow. Now, as I said, most of this is already proved. So the equivalence of the first two items that was already shown. And also the weak duality theorem actually implies that 3 implies 1. So if there exists a cut in the graph that has the same capacity as the value of the flow, then the flow must be maximum. And why is that true? Well, that immediately follows from the weak duality theorem, which actually said that the value of a flow, of any flow, is upper bounded by the capacity of any cut in the network. And if this is true, and we actually have equality here, okay, so we have a flow that is equal, or where its value is equal to the capacity of this cut here, there can be no flow that achieves a larger flow value. So the only thing that we are still that is still open to proof is the implication 2 to 3. So that means whenever we have an optimum solution, whenever we have a maximum flow, or whenever the residual graph contains no augmenting path, then there also exists a corresponding cut. So it's an existence proof here, which has the same capacity as the value of the flow. And that is what I'm going to prove next. Okay. So let us look at the proof. So once again, 2 says that the corresponding residual graph GF has no ST path anymore. So there is no augmenting path anymore in the residual graph. And 3 says something about existence of a cut, which has to have the same capacity as the value of the flow. So we have to define this cut, actually. And how do we define this cut? Well, we do the following. It's not so difficult. We define the set X to be all the vertices which are actually still reachable in the residual graph from the source vertex S. Okay, so for which there exists an SV path in the residual graph. And notice that because there doesn't exist any ST path anymore in the residual graph, so there is no augmenting path, the target node T is not in X. So that means this picture here is actually correct. So we have the set X on the left-hand side, which includes the source node and all the nodes that are reachable from S. And there is some right-hand side here which contains the target node at least, right? So that is all the vertices which are not reachable from S in the corresponding residual graph with respect to flow F. Now the most important observation, once you have this figure, is this one. Since all these vertices are not reachable, there is no arc here going from left to right, from x to x bar in the residual graph. So this arc here doesn't exist in the residual graph. So why doesn't it exist? Well, the only possibility is because it is saturated. So that means that the corresponding flow value along this arc must be equal to the upper capacity, because otherwise we still would have this arc, and then this vertex V on the right-hand side should be on the left-hand side. Now I want to argue that the capacity of this cut must be equal to the value of the flow, and that's now no longer very difficult to see. So the value of the flow, we already know that the value of the flow is equal to the flow from x to x bar, because x and x bar is actually a valid cut in the network. Now, by definition, this is just the sum over all u in x and the sum over all v in x bar, so this should be a capital X here, flow from u to v. But we just argued actually that for all such arcs that go here across the cut from left to right, we know that the corresponding flow value must be equal to the upper capacity, simply because these arcs are not present in the corresponding residual graph. So therefore, this is just equal to u from x, v from the complement of x, upper capacity of the corresponding arc, and that is just the capacity of the corresponding cut from x to x bar. And that's it. So once again, if we define this cut x and x bar in the way that we defined it, for all the arcs from left to right, we know these arcs must be saturated at the upper capacity. And for all the arcs in the opposite direction, we know there must be zero flow, because in both cases, otherwise we would get an arc from left to right in the residual graph. But this is not how this was defined. Now this ends the optimality proof, or the proof of these three equivalences, I should say. While this one is a so-called primal characterization of maximum flows, this one is actually a dual characterization of maximum flows. And I would like to finish with a short remark about the magic or the power of this dual characterization. Okay, so and in order to convince you, imagine you have computed a flow F, and you would like to prove to me or convince me, you would like to certify that your flow is really a maximal flow in this network. So if you just give me the flow, I might not be convinced, because maybe there's other flows that achieve a higher value, right? So how could you convince me that your flow is really maximal? So that would be a sort of optimality proof that I can also easily check. And the answer is simple. So next to the flow, you also deliver me a matching cut. And by matching cut, I mean the following: a cut that has as capacity the same as the flow value. Now I can very easily verify that the flow value is equal to the cut value. And I can also accept this as a proof, because I happen to know the weak duality theorem. So weak duality says that the value of any flow is upper bounded by the capacity of any cut. Everybody knows that. Okay, so since I know this, and you delivered me a flow and also a cut with the same value, I can accept this as a certificate, as a proof that your solution, your flow solution, is really the optimal solution, so that is really a maximal flow. And not only that, it's a certificate for the flow being maximal, but it's also a certificate, obviously, for the corresponding cut being a minimal cut in the network. Now, what for do I need the max flow min cut theorem then? Well, the max flow min cut theorem tells me or guarantees that such a certification is always possible. So for each flow, so for each maximum flow, there always exists a cut that achieves the same value. Okay, so there is always the possibility to certify your solution with a corresponding dual solution, which is actually the cut. So that is what the max flow min cut theorem tells me. It tells me that such a certificate, in order to certify optimality of a solution, always exists. That actually ends the lecture on maximum flows, the first lecture on maximum flows. Thanks for your attention. The next lecture is going to be about algorithms, and also efficient algorithms, meaning polynomial time algorithms to actually compute maximum flows. Thank you.